This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 94. Today's presentation, Using NOAA Satellite Data to Detect and Track Blowing Dust, will be presented by Bill Line, a physical scientist from the Regional and Mesoscale Meteorology branch of NESDIS STAR. Our facilitator today is Brian Mata, meteorologist with the Weather Service Forecast Decision Training Division, or FDTD. Just a few reminders before we get started that this session is being recorded, as you just heard. There's an opportunity for Q&A after the presentation, and we're particularly interested in questions and comments from our field offices and regional headquarters. So please post your question in the chat, and we will field them through there. Also, as you're asking a question, please use your full name or specify your full name when asking a question. If you're using an office account, that will allow us to follow up with you if necessary afterwards. We're always looking for future presenters. We are heading toward our 100th Satellite Book Club seminar. We'd love to have you be part of this weekly event. Please get in touch with us if you have an application to share with your colleagues. And the training team can help create training materials that may be unavailable or point you to materials that you may be unaware of. And Brian Mata, the Office of the Chief Learning Officer and our moderator for today, can help with any information on that. I'd like to thank the TowerS team, Kashad Bowman in particular, the Office of the Chief Learning Officer, the GOZAR and JPSS program, as well as all of you for being with us today. Without further ado, Bill Line is a physical scientist with the NESDIS STAR Regional and Mesoscale Meteorology branch in Fort Collins, Colorado. In his role, Bill conducts research into the detection of various mesoscale phenomena utilizing NOAA satellite data. Bill's a repeat presenter here at the book club. We're glad to have him back. Bill.
Thank you so much, Jordan, and thank you to the TowerS team for having me back, and thanks to all of you for joining today. This is a great audience, and I'm always happy to give these presentations to this group. If you've been paying attention to the weather in the West, or you work in the West and high plains, Southwest US especially, you know that it's been a very active period of blowing dust over the last couple months. So this is certainly a timely topic. So sorry, going along to the next slide. So this presentation, I want to talk about a few things, and if you like pretty animations, this is the place to be. Lots of great blowing dust animations here. But I really want to cover, kind of going back really briefly, the history of blowing dust detection and how we've gotten to where we are now, really highlighting some of those more traditional techniques first, followed by more advanced techniques that you should be leveraging in operations. Everything I'm going to talk about and all the animations I show either are available in AWIPS or can easily be installed in your AWIPS. So if you see anything you like that maybe you don't have and you want help with, it's very simple, and I can help you out with that. So shoot me an email or give me a call. Additionally, most of these products are available online on Sierra Slider. I also want to talk briefly about a blowing dust event climatology made solely off of satellite imagery that we've been working on, and will be a great resource to you folks in the field. So moving along to the next slide. Blowing dust is obvious relevant to the National Weather Service. It's part of the mission to detect and track blowing dust, and obviously especially relevant to the western half of the US, because it poses a hazard to both air and ground transportation, but it also poses a hazard to health. So just to cover some of the forecast products that are issued that might incorporate blowing dust to start, our forecast grids. To add blowing dust to the forecast, you might use satellite imagery to capture the spatial extent of dust and enter that into the grid so that it translates into the forecast, and of course communicate that via the text forecast discussions. Additionally, obviously, blowing dust poses a hazard to aviation due to restricted visibility, both at the local level and the TAFs, that's relevant, but also for the Aviation Weather Center, they're looking for blowing dust as and may cause them to issue SIGMETs. There are also the advisory and warning products. The more traditional blowing dust advisory and warnings are zone-based and typically longer duration now, while those shorter duration events, forecasters now have the ability, more recently in the last few years, to issue dust storm warnings. These are polygon-based. And finally, certainly forecasters, and I know you guys do a great job of communicating a blowing dust hazard to your partners in various briefings, but also on social media to the public, and satellite data is a great tool to be able to convey that message. So obviously, to get an idea of the degree of visibility restriction and really the quantify the impact of dust, forecasters, you're going to be looking at your surface METARs, and you're also going to be relying on people to give you those reports of just how much dust might be restricting visibility. But satellite imagery is going to come into play when you want to really convey and capture the spatial extent of that blowing dust hazard and how it's evolving in time. And really that's where satellite data gives you the advantage. So moving on to the next slide. I do want to just quickly note the importance. This is just another atmospheric phenomena where you're going to want to leverage mesoscale domain sector imagery, the 1 minute or 30-second imagery, to be able to capture blowing dust plume initiation as early as possible, additionally to track it in real time. There are various reasonings you might give for requesting a mesosector if it's not already available. Dust storm warning is specifically mentioned in the number 20 ranking criteria, but if you're going to have significant blowing dust events like this, you're probably going to have at least elevated or greater fire weather conditions. So keep that in mind, which that's level 8 ranking. So if SBC hasn't requested a mesosector for fire weather, you certainly could, and to be able to track hot spots as well as the blowing dust. So moving along to slide 5. First, as I mentioned, I want to talk about first the VIS and near IR based techniques, so daytime only techniques, but in relatively high resolution for detecting blowing dust. So on slide 6, we're going to start by just our basic, very basic traditional visible satellite imagery. Certainly you're able to detect blowing dust, and in this case, blowing dust along an outflow pushing south across Nevada in June of 2020. However, when you have lots of clouds, you have smoke, etc., this grayscale single band visible imagery, it's going to be hard to really pinpoint exactly where your blowing dust is. You get a good idea of where the dust front is, but it might be trouble detecting exactly where dust is elsewhere, given the clouds, smoke, etc. So we want to do a little more and really get away from using just the single band imagery, especially for blowing dust detection. So on slide 7, we take it a step further, and really you want to be looking at during the day, if you're leveraging your higher resolution visible near infrared imagery, certainly you want to leverage true color imagery. And in this case with GOES-R, we have geocolor, which is pseudo true color product, of course, given the absence of the green band, but it does a great job. And you could really see the difference in that with atmospheric aerosols, your blowing dust, of course, is appearing more tan to browns, while your smoke with smaller particles scattering and shorter wavelengths is going to appear more of a grayer shade. So much easier to differentiate dust from smoke here, as well as from clouds. And so on slide 8, you might want to move to maybe more advanced or products that show a little more than just the aerosols, like in geocolor. So RGBs such as a dayland cloud fire RGB, which is available in AWIPS, but even I think better than that is the natural fire color RGB, which is easily added to AWIPS, or you can look at it on Zero Slider, which replaces for dayland cloud fire RGB the 2.2 with the shortwave IR band to better highlight wildfires, along with the veggie band and red vis. You really get a good picture of and a differentiation of clouds from dust and smoke, but also highlighting the wildfire hotspots. And this was a great case from Midland. You could clearly see the outflow boundary emanating from the thunderstorms with a large opaque dust plume associated with it, causing a significant wind shift and visibility restriction on that fire. And this was a great case of the Midland office leveraging satellite data to communicate to partners on the fire of that incoming wind shift and visibility restriction. So from the reflectance channel standpoint, you have your traditional visible imagery, but really take it a step further during the day if you want to look at the higher resolution data and leverage things like geocolor and these RGBs that capture fires and dust. So on the next slide, I do want to touch on the importance of forward scattering during the daytime because it is really important for aerosol detection during the day. Obviously, specifically if you're using those reflectance channel, the VISs, the near IR, geocolor, and some of those daytime RGBs. It's important if you have access to both GOES East and West to really pay attention to what time of day you're leveraging the data. And I won't go into too much detail here, but in general, in the morning, you're going to want to leverage GOES West if it's available, because as the sun rises in the east, you're going to have that added forward scattering component into the satellite sensor that's going to really add to that dust signal and make it appear a little better than from the GOES East sensor, because the forward scattering is really enhancing the dust signal, especially with the low sun angle. In the afternoon, that's going to flip as the sun's setting in the west. Afternoon to early evening, you're going to want to switch to GOES East, again, because now you're having forward scattering into the east sensor, enhancing the dust signal. So again, summary: morning GOES West, afternoon GOES East, especially in the west where you have both CONUS sectors, but you might have two mesosectors over the features. So you're going to want to flip-flop if you can. And so on the next slide, I have an example of this. So this is a morning blowing dust example from late March this year. And we had mesosectors from both GOES East and GOES West over the southern high plains, capturing wildfires and blowing dust. And you could see in the morning, prior to 18Z from GOES West, you could clearly see the blowing dust plumes starting and spreading east, northeast, while from the GOES East perspective, again, much less forward scattering. You can't really see the dust at all if you're not knowing it's there, and you'll probably see some movement there eventually, but in this case, you would want to, as the sun's rising in the east morning, you're going to leverage GOES West for tracking blowing dust, and that's with these reflectance channels and products, not IR products. So on the next slide, same day, going into the evening hours, just a little further south, West Texas, eastern New Mexico, you could see from GOES West the dust and smoke. You could kind of see it, but the view of the dust and smoke is much clearer from your GOES East perspective. So as the sun's setting in the west, you're looking at the dust from GOES East. You have that added forward scattering helping to enhance that reflectance signature. And this is a good example also of showing how a product like geocolor does help to differentiate your smoke plume coming out of that fire along the border versus what's blowing dust. On the next slide, I also want to give a word on parallax and continuing the importance of, if you have access to both GOES East and West, leveraging both of those satellites and leveraging imagery from both. Here over in Nevada, looking at widespread thunderstorm activity, you could see outflow boundary pushing a area of really thick dust west, where I have it highlighted there in that animation. And it's very clear in GOES West. However, if you were simply using GOES East with this event on slide 13, that same region, of course, you don't have 1 minute imagery here, but also it's a good example of showing how the thunderstorm activity due to parallax is masking that blowing dust plume, especially early on as it gets going. you're not able to see it from the GOES east perspective. Sorry, that should say GOES east. So again, look at both GOES east and west, especially when you have thunderstorms, so that, because tall clouds might be masking the view from one sensor. So along those same lines on slide 14, just another word on the importance of leveraging 2 GOES satellites is for wildfire hotspot detection. If your office is in the business of detecting hotspots from satellite imagery and reporting those to your partners, if you have access to both GOES east and west full resolution imagery, use both, especially if you have cloud cover in the area. Because in this case, you had a clear view of this fire near Estes Park in Larimer County, Colorado. You had a clear view from GOES west. However, those mountain wave clouds were masking the view of that hotspot from GOES east. So from GOES east, there was actually no thermal signature, while GOES west captured the hotspot really well. So again, definitely pay attention to both satellites if you have access to them for both dust events, really any event where you're trying to track or detect a feature close to the surface. Next slide. Now we're going to move on to the IR-based techniques, so we're not as concerned with forward scattering, but you might still have concerns about features blocking a signal, so still pay attention to that. And we're going to highlight both the split window difference and then RGBs, in which of course the split window difference is an important part of. So on the next slide, really briefly covering the split window difference for blowing dust detection. I have a chart there, but in summary, in the clean window IR bands, those shorter wavelength, long wave IR bands, so around 10 micrometers, are going to be basically more sensitive to blowing dust, lofted dust. Especially, you can see in the chart, a moderate dust load is going to cause that brightness temperature to be cooler than at the longer wavelength, long wave IR bands, such as around 12 micrometers. So that when you take a difference between the two, 10 minus 12 microns, you get a near zero to negative brightness temperature difference signal for lofted dust, which contrasts with a background scene that's typically 0 to positive for a clear sky or even clouds. And there's a similar sensitivity to lofted dust with the cloud top phase band, so around 8.5 micrometers. That band's a little more dependent on dust composition, but also tells you more information about cloud top phase. So you'll also see this band in some of the multispectral products. But really, the split window difference is the keystone to most of our IR-based techniques for detecting blowing dust. And in the examples I'll show, I like the grayscale color table with the darker grays to blacks representing your negative values of split window difference, so more likely blowing dust, versus the lighter grays to whites, which are not blowing dust, maybe clouds, clear sky, etc. So on slide 17, I do want to quickly go through the split window difference through the years. Some of my studies have been looking at a climatology, and we start around 2000, so that's why I'm starting with the GOES 8 through 11 imager. Did have a 4 kilometer 10.7 minus 12 micron split window difference, and you can see an example here. These are all just hourly images, but a very good capability with the split window difference from the mid-90s through about late 2011 to be able to detect lofted dust with this technique out west. However, when we went on to late 2011 to early 2017, on the next slide, unfortunately, we lost that dirty window IR band and the ability to compute the split window difference on the imager. However, we did still have those channels on the sounder, so we could compute and display sounder imagery split window difference at much lower 10 kilometer resolution. So you can see in this animation, the darker areas, you could still detect blowing dust in this period, but I know you're missing those smaller scale events and maybe the start of the larger events. But fortunately, come early 2017 with GOES-R, on the next slide, we got our dirty window IR channel back, and we're able to have our split window difference back, now at 2 kilometer resolution. So moving to the next slide. Just another example of split window difference for dust detection. It's going to give you the capability day and night. And this is an example of a display you might make in AWIPS, is to overlay IR window cold brightness temperatures on top, maybe to mask some of those clouds to better differentiate blowing dust where you might have clouds causing difficulty detecting those dust plumes. On slide 21 now is moving on to more multispectral techniques for blowing dust detection. So can you go back one, Kushad? I mentioned what split window difference is good by itself, but it's really, you're able to see the darker areas and what might be blowing dust. But if you have a lot of clouds or it's a faint dust plume, it might be more difficult to really confirm whether it's blowing dust or maybe some other feature. But if we bring in other channels, we could highlight features in the clouds and really focus in on what's blowing dust and what's not. And that's where the RGBs come in. So on slide 21, we have the traditional dust RGB, which is available in AWIPS and combines the split window difference with cloud top phase and IRW. And I think this is great for forecasters. I see a lot of offices leveraging this product. However, I know personally that folks with colorblind issues cannot see blowing dust at all in this. It has very little contrast in the dust feature, and it's very difficult to detect blowing dust. And I know, talking to people without color blindness, it's tough too. So I've been working to create a alternative RGB on slide 22 that uses those same ingredients, but just switches things up to make the blowing dust more obvious to people with colorblind issues. But I've been told people without colorblind issues can see the dust a lot better. Here where Kashad's highlighting it, but coming out of West Texas, Southwest Kansas, and there's some plumes in Western Arizona as well. But you're also maintaining the ability to differentiate cloud types as well. So on the next slide, that's just a comparison between the split window difference, where you could see the plumes highlighted as grays, and then the two RGBs where the clouds are further differentiated with the addition of those other bands, and the dust gets highlighted. On the next slide, 24, this is an example of really a messy scene, lots of clouds. This is from yesterday, actually, across the Southwest US, where using the split window difference alone might make it difficult to detect blowing dust. But that second dust RGB I showed, and there on the right, you could see the dust highlighted as shades of yellow to grays at times, really being differentiated again from the clouds. On slide 25, another RGB that might be important for folks in the West who are interested in detecting blowing dust. On those days, you're probably also interested in detecting wildfire hotspots. So you could create a simple RGB that combines a split window difference with the IR window and shortwave IR to detect not only blowing dust as the greens, but also hotspots. And this RGB show up nicely as red pixels. So on slide 26, there's another example, side by side, of the split window difference on the left and that dust RGB on the right. You could see the broad blowing dust plume moving north across West Texas, while there are hot spots across most of the eastern half of the domain highlighted as red. And this is another RGB that I've created and kind of really perfected over the last couple of years. And if you do want it, it's easy to install, and I could help you with that. So on slide 27, I do want to say a word on the incorporation of the derived aerosol product as well. If you're a Satellite Book Club regular, you heard me talk, I think a couple months ago, about the new GOES-R RGB and derived product readout menus. And there are two options for dust detection. The dust RGB and the split window difference product have the aerosol dust product as readout. So if you sample the RGB, you can see what the dust algorithm says in terms of how confident it is that there's dust. On slide 28. All right, now we're going to talk about more advanced dust algorithms and maybe where we're going in the future with dust detection. On slide 29, we have the Deborah dust product some of you might be familiar with. It's available on Cirrus Slider, but I know some Weather Service offices have it in AWIPS as well. really, this is an especially good product, I think, for sharing with the public or in briefing packages, in that it highlights blowing dust as yellow versus everything else that's grayscale. And this algorithm combines those IR techniques with some other really intelligent tests to really try to focus in and highlight dust. I will say it oftentimes it misses the more faint, less obvious blowing dust events that you'll still want to then leverage the other tools, but really great for briefings and social media. And also if you just want to have it running to really capture your attention when there's blowing dust. On slide 30, I think where we're going in the future with things like geocolor is imprinting various signals of various features on a single geocolor-like animation. And this is one that you could create in AWIPS right now, but basically you have geocolor as your base layer, you have some sort of dust overlay highlighting the dust, in this case as yellow, and something about fires, maybe one of the fire products highlighting the fires here as red, and then you have GLM as well. So trying to put as much as we can in one animation to really save on your screen real estate. On slide 31, we're getting to the end. I do want to talk about VIIRS quick. We have on the left 375 meter daylight cloud RGB, and on the right natural fire color RGB. I think where VIIRS comes into play is if you really want to focus in on exactly where those plumes are originating, or where maybe the densest part of these plumes are, that high resolution VIIRS is going to give you that added spatial detail to really focus in on those plume origin points. On slide 32 is a nighttime example where you might leverage the day-night band near constant contrast product to give you a higher resolution nighttime view of exactly where a dust plume is, or maybe where a front is with blowing dust behind it. The detail on that near constant contrast product will be able to highlight the dust. On slide 33, I mentioned social media. I think you Southern Plains offices in Southwest US do a great job of communicating the blowing dust hazard using satellite imagery. And satellite imagery, again, is a great tool for showing the spatial extent of blowing dust and where it's moving. A lot of examples of Deborah dust being used on social media, but also geocolor are very intuitive. And also it's neat to see the RGBs being used to communicate blowing dust. If your public can understand what those RGBs are showing, I think that's great too. Going on to slide 34. Quick word on the blowing dust climatology we're building, because I think it is going to be relevant to you folks. We're analyzing hourly images from 2001 to 2020, primarily split window difference, but also some VIS in there, and primarily GOES, but some MODIS and VIIRS too, to highlight blowing dust events across the Southwest US and the Southern High Plains. And really this allows us to identify various geographic trends, temporal trends, and meteorological trends, and when, where, and why blowing dust events occur. On slide 35, you could see the monthly distribution, April and the spring being very popular times for blowing dust. But as you get into the summertime, the weather pattern shifts north and the monsoon sets in. From the satellite perspective, we're not going to capture as many blowing dust events with an abundance of cloud cover. I think the satellite techniques are going to capture more of those synoptic scale blowing dust events, while the thunderstorm initiating blowing dust will be better served being detected with ground-based networks. However, spatially, we're able to see everywhere, so we could capture blowing dust if they occur from the clear sky. So on slide 36, one more animation showing time of day. In this data set, again, these are preliminary results, blowing dust peaking around 18Z. Probably part of this is, and this is start time for dust events. As you get into the afternoon and cloud cover increases, we're probably missing events with this data set, but still a great data set to capture trends in when and where blowing dust happens. So more on that in the next year or so. And going on to slide 37, that is the end of my presentation. Again, if there's anything you saw in this presentation and you have questions about or want access to, please shoot me an email. And at this time, I think we certainly would like to talk about any questions you have, especially operational challenges you might have related to blowing dust detection. Thanks for listening, everyone.
All right, thanks, Bill. Let me encourage folks to stay on for the Q&A period. We just have a couple of announcements to get to first. Lee is going to post a survey link in the chat room. If folks have feedback or other comments that they want to give to the team, please use that vehicle to do that. And a week from today, on Thursday, April 28th at 12 p.m., the usual time, Michael Bowen from NWSFO Tulsa will discuss the mesoanalysis of the February 24, 2022 convective winter precipitation event in eastern Oklahoma and northwest Arkansas. Also, if anyone has questions about the satellite products or configurations, you can contact the Tower S team, Lee Byerly and Kashad Bowman, and they will help you out. And without further ado, if you haven't already put your questions into the chat room, please do that now. I know we've got a couple in the queue here, so we can get started right away. Let's see, a comment from Bill Schoberg says, don't forget that there are 2 VIIRS, and with the swath width, you can get multiple passes from each one.
Yeah, Bill, definitely, and really over the CONUS with 2 VIIRS, 3 to 4 swaths over a location, so you could get an idea of the evolution of that blowing dust with the high resolution imagery. Thanks for that comment, Bill.
And Scott Lindstrom has a question. Do satellite signals always mean surface visibility restrictions?
Yeah, that's a great question, Scott. And a couple things on that. First, with our climatology data set, I think that's something we'll be able to do is focus in on several cases or a bunch of cases, and then look at the nearby surface obs and see if they always had a visibility restriction, or if there's some sort of connection between what we see in split window difference and what's happening at the surface. My guess is not always, especially as you get far from the source region and that dust maybe becomes lofted. But again, I think our study can maybe look at that a little closer.
Yeah, so part 2 of Scott's question is how common is dust lofted above the surface, and would lofted dust versus non-lofted dust give a similar signal?
Okay. Maybe I'm not understanding your question, but all of these events have dust that's lofted above the surface. So I think the question is if the dust is completely off of the surface, which I don't have an answer for you, but yeah, with all these events, the dust is in the air, moving away from some sort of source point where the dust came off of the surface.
All right, Paul would like to comment on discerning visibility from satellite data.
Go ahead, Paul, or did you have something you wanted to say?
Yeah, Bill, good presentation, thanks. This is Paul Enegath, the Sioux out in Phoenix. I guess I'd kind of be curious your thoughts a little bit on going off of Scott's question as well. I think one of our biggest challenges is, we see the dust. I think we're pretty good at picking that up off the satellite data. The challenge is really always just how bad is it at the ground? What's the visibility like? So Scott's question kind of gets into that, but I wanted to kind of ponder with the climatology stuff you're showing and starting to build as well, if there's not some opportunity to do, I don't know how far in the distance this might be, some kind of like machine learning application, or trying to, get some kind of probability that there's actually dense dust at the ground, because that's really what's more problematic is, especially for like ground transportation stuff, whether it's fog or dust, you don't really start to have a problem until the visibility gets down to like a quarter mile or less. More than that, it's nuisance and air quality issues, I would say. But as far as immediate impact outside of aviation, it's got to be a lot denser than that. So What can satellite data do for us, I think, on that, or what might be coming to help with that?
Yeah, Paul, thanks a lot for those comments. And it's really great to hear from the field that these are your challenges, and really that could help drive what we want to do, where we want to go with this kind of research. And again, yeah, I think with such a robust data set that we're building of confirmed blowing dust events, we'll be able to do things like, how do we know, can we get information from satellite that tells us exactly what it's like at the surface? But also, thanks for bringing up your point on machine learning, because since we're going to have such a robust data set for blowing dust events, we could maybe leverage that, yes, to maybe train some machine. I'm no machine learning expert, but we're talking to people at Sierra who are, to leverage this data set to maybe help develop a machine learning model to aid in that detection. And yes, connecting that to what we're seeing at the surface to better highlight, to better provide information to you in the field if what we're seeing in satellite is causing an impact at the surface. Because as I mentioned right now, I think satellite, yeah, like you said, it's really good at giving you the spatial extent, and maybe if you're drawing polygons, to help draw the polygons, but can we take it a step further? And I think that's what we want to be looking at. Thanks, Paul.
All right, next question from Michael Jamakowski. Is blowing sand different with respect to satellite detection?
Yeah, great question, Michael. I think when we say blowing dust, we refer to any lofted mineral, sand or what have you, dirt. But it does I think in split window difference, it's pretty uniform. As I showed, there's been a lot of studies showing the appearance based on the composition. For the most part, split window difference is consistent, but things like cloud top phase, bringing that in really helps to differentiate what the material is that's being lofted. I do know White Sands National Park or Monument or whatever it is, I think the signal, it doesn't show up as well in the split window difference product, but I think is highlighted, obviously in reflectance channels. So then that's something else definitely that we're looking at, and to make sure that we're able to detect all types of lofted minerals. Thanks, Jammer.
All right, thanks. Liam asks, how well do these techniques work to capture Saharan dust events in the Atlantic Basin?
Yeah, really well. A lot of the early studies through the 90s were looking closely at the Saharan dust and moving over the ocean, and these techniques are really, I think, highlight dust a lot better over the dark background ocean. So definitely good. And I've been also developing, I didn't show them here, but products to really hone in on situations of Saharan dust over the ocean, but also where you have a lot of moisture and water vapor in the atmosphere, because that makes it a little difficult using this technique. So over the US, when we're detecting dust, usually it's a dry atmosphere, but as we know, the dirty window IR channel is sensitive to moisture. So when we introduce moisture, this technique becomes a little more difficult. So that is something else we're working on. Thanks, Liam.
All right, next question. Jordan asks a slight variant of Paul and Scott's questions. In your analysis and maybe experience, is the magnitude of the dust shortwave difference correlated with visibility reduction?
Yeah, split window difference correlated with vis reduction. That's a great question, Jordan, and we haven't gotten to that yet. We've been focused this time around on identifying the dust events, but I think the next time around, maybe we could, try to correlate magnitude and the simple split window difference with something at the surface, especially close to the dust source. But thanks, Jordan.
All right, next question is from Mike Stavish. He says, I've seen a few events creep up on us, and being prepared to have a dust product going is good, so you might catch it and advertise it early. Do you look at the ARL dust model or other like tools?
Thanks, Mike. I haven't. Someone working on this project with me has been looking at ARL. With our climatology work, though, I do hope to develop, composite maps of meteorological fields, and we could focus that geographically. What conditions, larger scale conditions, are most conducive to these blowing dust events, so that, yeah, you could look a week out or several days out and have a good idea if blowing dust is going to occur. So I think in terms of forecasting events, our climatology moving forward, hopefully we'll be able to aid in that effort. Thanks, Mike.
All right, last question, unless we get another one. Dan Lindsay asks, Paul or anyone more familiar with surface stations and METARs, are METAR obs of blowing dust with reduced visibility reliable?
So I'll go first, and then maybe someone else could supplement, but because we've been looking at METAR obs in the study, and an ASOS does not detect blowing dust. I think it would be recorded as haze. So in order to have the blowing dust code in there, you would have a human, so maybe some sort of weather observer at certain airports would manually have to supplement the ob with blowing dust. So where you have those observers, I think they're reliable because it's a human entering, but obviously those are coarse spatially. Paul, do you want to? Paul did comment. Brian, do you want to read Paul's?
Yeah, Paul commented that they are quite reliable in his experience. So,
but commenting that those obs are spread out widely, which brings in the importance of satellite data to fill in those gaps.
Right. And another comment from Mike Lawson in southern Alaska. They get both glacial silt and resuspended ash that can be detected using the dust products. So it may be worth looking at a couple of products or cases in the future, mostly for air quality concerns.
Mike, yeah, thanks a lot for that comment. And I think the TowerS folks are going to send me these questions and comments, so it'll be great to have this on record.
Yeah, so Bill, one last question. If you were starting to look at an event, what product would you look at first?
I think most reliable, day, night, not having to worry about which your satellite viewing angle or forward scattering. I would rely on an IR-based RGB, I think, whichever one you like and whichever one you could see the dust in. So for me, I would be looking at that dust RGB I created because I know it's going to pick up on dust if it happens, but at the same time, I'm able to mask out the various cloud types. So the IR-based techniques I would rely on first and foremost for having a confident blowing dust detection tool.
All right, thanks, Bill. Let's toss it back to Jordan.
Thanks, everyone, for the great questions.
All right, outstanding presentation, Bill. We're always glad to have you here at the Satellite Book Club, and thanks to Brian for being our facilitator for today. We had a lot of good questions. Really appreciate that. The Satellite Book Club continues next week at our regular time, 12 noon Eastern Time, Thursday, April 28th. We have another former satellite liaison, Michael Boland, now a meteorologist at the Forecast Office in Tulsa, Oklahoma, is going to provide a meso-analysis of the February 24th convective winter weather precipitation event in eastern Oklahoma and northwest Arkansas. So I know we're moving out of winter now, but that'll be a good recap. If you need help configuring satellite products, the TowerS team is available. Just reach out to them. Their email address is there. We got John Evans and Lee Byerly. We have a great team. Also, as I mentioned earlier, Kashad Bowman is able to assist with any questions or comments you have about the Satellite Book Club, including if you would like to present. We would love to have you, particularly if you're at a field office, to provide your perspective. All right, well, thank you so much for joining us today. I hope you stay well, and we'll see you again next week. Take care, everybody.